Okay, in this semester, we start with an integration. That is an anti-operation of differentiation. So let's take a look on some of this basic idea about the antiderivative. And in the last semester, we actually focused on given the function, say f of x, and try to find its derivative. So this item, the function was given, and the question is, what is the derivative for this particular function? Okay. And now in the integration topics, we do the opposite direction. Instead of finding the derivative, we give the answer of the derivative and ask you which one is the function that we begin with. Okay. So for instance, if we say the derivative is 2x, and the question is, what is f of x? Okay. So that is, say, f prime of x is equal to 2x. And what is f of x? So that's the question we are going to answer in the integration technique. And basically that's the idea. Okay. And of course, from our previous experience, we know when f of x equal to 2x x squared, and the derivative is 2x. Okay. So for the answer we ask in here, if the derivative is 2x, then f of x must be x squared. Okay. And we might wonder, is this the only solution or not? But basically we know this is at least one of the solution. And we name this function as the antiderivative of the function we given in the very beginning. Okay. So the formal name is, since the derivative of x squared is equal to 2x, and we will say x squared is an antiderivative of 2x. And here we focus on 2x n indefinite, because it may not be the only solution, but it is one of the solution. Okay. All right. Now we pay more attention about the antiderivatives. And formally we will define. And because of the more easy to identify, we will use capital F of x as the beginning function, and its derivative is the locus of f of x. And so the other word, we will say capital F of x is an antiderivative of locus of f of x. Okay. And of course, provided the capital F of x take a derivative equal to locus of f of x for all x in our domain we interested in. Okay. Now back to our previous example. If a function is equal to 2x, and what will be the original function of the derivative? And we know the answer, one of the answer is x squared. So we will say f of x, x squared is an antiderivative of 2x. Okay. And we might link this to the formal definition. X squared will be named as the capital F of x, and 2x will be named as locus of f of x. All right. So you can double check. Since x to the power 3 plus 2x plus 1 take a derivative equal to 3x squared plus 2. And therefore, we will say the capital F of x equal to x to the power 3 plus by 2x plus by 1 is an antiderivative of 3 times x squared plus 2. Okay, so this locus will be corresponding to the function after derivative. The capital F of x will be the function before the derivative operation. Okay, and since you can treat as the opposite operation of the differentiation, so we will call the capital F of x as an antiderivative. All right, now here we have another example. Okay, and capital F of x equal to 1/3 of x to the power 3 minus by 2x squared plus by x minus by 1. And its derivative, we can do that turn by turn. 1/3 as the coefficient, and x to the power 3, we use power rule, bring down the 3, and with 2 left in the power. So we have 3 times x to the power 2. And minus by 2 is a coefficient, and x squared after derivative is equal to 2x. And after derivative for the x, we have 1. And minus 1 after derivative is equal to 0. And after combining, we have 1/3 times 3 become 1. So the coefficient for x squared is equal to 1. And the coefficient for x will be minus 4 and plus by 1. So we already showed that the capital F of x, which is 1/3 of x to the power 3 minus by 2x squared plus by x minus by 1 is an antiderivative for x squared minus 4x plus 1. And in this example, we will see to show a function is an antiderivative for the other function, you better do the derivative for the first one and match the result with the second function. Or we can say we take a derivative for the capital F of x and to see if its answer is equal to locus of f of x. And if this is true, then we can say capital F of x is an antiderivative of the locus of f of x. Okay, so it seems pretty easy to verify. Okay, now in order to have a better idea about what it is about the antiderivative, we try to give you some examples. Okay, for instance, here we have a capital F equal to x. Then the derivative is equal to 1. Okay, now if g of x equal to x squared, x plus 2, so the derivative is equal to 1 plus 0, which is equal to 1. And how about h of x, capital H of x? That's x plus c. C is a constant. That means a number. It's not a variable, simply a constant that we do not specify what that constant is. However, it is a constant. Could be -3, could be 5, could be 2.1, or any given number. So the derivative for capital H of x will equal to 1 plus 0 is equal to 1. And we find that all these three functions, capital F of x, capital G of x, capital H of x, they all share the same derivative, which we name as locus of f of x. Okay, so all of them are antiderivatives of f of 1. Okay, so here we have f of x, g of x, capital G of x, capital H of x, are antiderivatives for the function f of x equal to 1. Okay. And from this example, you'll see that antiderivative is not unique. As long as the function has the same core part, we thinking about the x as a core. And even though their plus constant are different, they all have same differentiation result. Okay, say all of them are antiderivative for the function we given with at the very beginning. Okay, so that means when we say what is the antiderivative of f of x equal to 1, our answer may not be unique, because you could say capital F of x equal to x is an antiderivative for 1. You can also say capital G of x equal to x plus 1 is an antiderivative for 1. And you can also say capital G h of x equal to x plus c is an antiderivative for f of x equal to 1. Okay, and all of these three, or actually even more, they are all antiderivative of f of x. So how can we kind of come up with a notation that we're not confused with those more than one solution? Okay, so let's take a look for the previous example and even more different constant c. So in this figure, you can see we have constant c equal to -1, equal to 0, equal to 1, equal to 2, equal to 3. And if you plot, we see those functions actually represent the line in a coordinate plane, and this line are parallel to each other, and they share the same slope, because the slope is the derivative for this five functions. Okay, that means even though those antiderivatives may not be the same, but their core part are the same, and they only differ by the constant differences. Okay, and that gives us a formal definition of the theorem in the following. And since all this antiderivative for the given function has the same code, so we can pick out any of them as their one of the antiderivative, and all the others can be expressed almost the same form and plus a different constant. Okay, and that's the idea for here. So in this sense, tell us that let G be an antiderivative for a given function lowercase of f(x) on an interval, then every antiderivative capital F of lowercase of f on I must have the same form, namely they have the same core part and differ by a constant c. Okay, and that means even though we do have more than one antiderivatives for any given function, we only need to find one and then express all the others by a plus c constant. Now in this example 3, we can use that one to show this. Okay, and in this example 3, we pick up the one of the antiderivative from the previous. Say capital G of x equal to x squared and the derivative is derivative equal to 2x. So we know capital x squared is an antiderivative for 2x. Okay, and then we use that one as a copart, and all the other possible antiderivative for 2x can always express in terms of x squared plus c. And here the c is any constant. Okay, so in this case, the core is x squared, and plus c can be provided by different c in order to come up with different possible solution for the antiderivative. Okay, and in the coordinate, when we plot those antiderivatives, they all has the same parabola form and only differ by their y-intercept. Okay, now we formally define indefinite integral using the antiderivative idea. Okay, so here's a format. The basic information is capital F of x is an antiderivative for f of x. Okay, so capital F of x plus c basically will be the form for all possible antiderivative for the locus of f of x. Okay, since we will treat one of the antiderivative we found as the copart and plus c to represent all other possible antiderivatives. So in our left hand side of the equal sign here represent format of the of an antiderivatives. Okay, and to indicate this antiderivative is coming from the locus of f of x, in the left hand side we use locus of f of x and use dx to indicate this is a variable. We do the derivative, and in here we do have a sign. It looks like could be I and or could be the S. Okay, and we use this one as an antiderivative expression. Okay, so we use integral sign f of x dx as the antiderivative for antiderivative, and then we use the result that we really come from the very beginning, capital F of x plus c. Okay, all right, and so from this expression we must have a link. The capital F of x is an antiderivative of f of x, therefore derivative of capital F of x will be equal to locus of f of x. Okay, so with this link we can express all the antiderivative for locus of f of x by integration sign f of x dx and equals to capital F of x plus a constant c. Okay, so we formally using this sign to represent the general format for the antiderivative. and this is also known as the indefinite integral. Okay, and right in here, couple terms. First, the integral sign. That's the part in here, the yellow mark. And the blue mark, f of x, is also known as the integral. And dx is because we are doing the derivative, even though this is an antiderivative part, but still come from the derivative. The variable we're doing the derivative xx. Okay, and we have to clarify, or at least identify, which variable we're doing the derivative is, because in the further chapter, further advanced chapter, and I believe it's chapter 8, we are going to do the function with more than one variable, at least two variable functions, and we are going to do the derivative and also the antiderivative. And in that situation, we have to specify which variable we deal with the derivative. Okay. All right. And the constant c is also known as constant of integration. All right. And now with this notation, say the antiderivative for locus of f of x and we're looking for its one of the antiderivative, the core part, which is the major issue that we are going to deal with in this chapter 6. That is, we are going to find one of the capital F of x and fit it into this box, and then we are going to plus a constant c in here. Okay, so this will be, let me use the red color. So this is really the major job. We are going to find the capital F of x for any given locus of a function f. Okay, and since some working experience can help us, so we will write this kind of experience as the rule. And so in the following, we are going to introduce some of the integration rules, and we name this as the basic integration rules. Okay, so one of the first one, since we know for any constant k times x after derivative with respect to x is equal to k. So capital K, sorry, not capital, k of x is an antiderivative of k. So we use antiderivative format, or the indefinite integration form, integral sign times the locus of f of x, and dx indicate the variable we deal with, and this is capital F of x, and of course plus a constant c. Okay, and that means the antiderivative for constant is actually the constant times x and plus some unknown constant c. Okay, and these two must be linked. All right, now right here, antiderivative for 2x, and we know one of them is antiderivative for 2, and we know one of the antiderivative is 2x. So 2x is the copart and plus a constant c. So we complete the antiderivative or indefinite integration process for this particular example. Okay, now the second one, pi square dx. Pi square, even though it looks like a power form, however, pi is a constant. So pi square is simply 3.14 times 3.14, and you don't have to multiply to come out with a decimal expression. We all know this is a constant. So we can apply the constant rule as we introduced. So pi square has an antiderivative pi square times x. So you will say indefinite integration of pi square is equal to pi square times x plus constant c. Right. Okay. And rule number 2 here, we try to figure out what is the antiderivative for x to the power n. So in this case, we're looking for f of x, capital F of x, such that its derivative is equal to x to the power n. All right. So we check on our left hand side. This is capital F of x, and after derivative, 1 over n plus 1 will be the constant pull out, and x to the power n plus 1, use the derivative power rule for the derivative. We bring down x plus 1, n plus 1, and in the new in the power part, n plus 1 minus by 1, and after cross away n plus 1 from numerator and denominator, we have a 1 as constant. So we do find out that (1 over n plus 1 times x to the power n plus 1 is an antiderivative of x to the power n. Okay, and that is the power rule. And in this expression, we notice that n plus 1 is in the denominator. And that means you are not be able to have n equal to 1, n equal to negative 1. Okay, because when n equal to negative 1, then you have 0 in the denominator. That means the power rule for the basic integration rule will not satisfy when n equal to negative 1. Okay, and or we may say antiderivative for 1 over x has not been defined yet from this power rule. Okay, so the power rule can apply to all kinds of x to the power, but not for x to the power negative 1. Okay, because x to the power negative 1 is equal to 1 over x, so it's not applied for antiderivative for 1 over x. Okay, and let's try some examples. And since we know the power rule pretty much focus on the power, as long as you recognize the power, you can apply to the power rule n plus 1, x to the power n plus 1 as the core part. So right here, we try to find the antiderivative for x to the power 3. That means n equal to 3. So n equal to 3 plus 1 become 4. So we have a 1 over 4 times x to the power 4 as a core part and plus constant c. And the second one, we pretty much recognize that n is equal to 3/2. Okay, so 3/2 plus 1 is 5/2. So we have 1/5/2 times x to the power of 5/2. Or flip down, become 2/5 times x to the power of 5/2. Okay, and how about this one? Okay, so first we rewrite, and the denominator power become negative. So n is equal to negative 3/2. Okay, and n plus 1 become negative 3/2 plus by 1 is equal to negative 1/2. So we have a 1 over negative 1/2 times x to the power negative 1/2 plus constant c. And flip down, we have negative 2. So the solution for this antiderivative is negative 2 over x to the power 1/2 plus a constant c.